Okay, I guess it's 4:10, so we should start. Hi, welcome to the new masterclass that we have today, talking about continuous improvement with no other than Gianluca Pagani from Georg Fischer Precast Additive, someone that I really admire in terms of their work and actually specifically Gianluca in terms of his knowledge. Every conversation with him has been really, really nice, and always I've learned something personally. So that says a lot. I have to admit, Gianluca always surprises me very positively. So today, just like in the previous masterclass, the two people that are going to be teaching you are me. I have a background in metal AM for almost a decade now, and I've worked with a lot of customers in terms of bringing their production to good TRL and helping them in qualification and R&D processes. Gianluca, on the other hand, is someone that is been working at Precast for quite some time. The company has changed hands a few times, and now Precast Additive is a part of Georg Fischer. They have a lot of systems that focus on aerospace quality, and they are, Gianluca's experience has been coming from investment casting, where he is an expert, and I can really say that with a capital E, in post-processing of components. And he is also now the production manager at Precast Additive, where he's led the internal efforts to become the first organization that has NADCAP certification in Southern Europe for metal AM, which is a really big deal, and we'll get into that in a second. So our topics today is going to be a 30-minute discussion like last time. You can ask questions at any point, and then there will be a 10-minute Q&A, which tends to run a little bit longer, depending on the complexity of the questions and whether we can address them in such a short session. But if you can't, then you can always book a feedback session one-on-one for 30 minutes, especially if you're not an extrovert and you don't feel comfortable talking in a big crowd, or if your topic is a little bit more complicated where we have to get into some more details and assumptions behind the scenes, because of course we can't go over everything in one of these 30-minute master classes. So the first thing that we'll talk about is what is continuous improvement, and then get into how to use Kanban, which is a method of continuous improvement in metal additive with value stream mapping. That's something we've gone over before in the last masterclass, so maybe you can refer to that and watch that in your free time. And then we're going to talk about how to actually do Kanban in metal additive and how to utilize the FMEA in metal additive for this purpose. And then we'll actually switch it to Gianluca, where he'll give us an introduction to his company and also the efforts that he's gone through in metal additive. And then we're going to ask some questions that I've gathered from the class offline. And by the way, your questions were fantastic. It's actually helped me think about the solution in terms of how to present this in a slightly different way. And we will address some of them. Some of them were a little bit on different topics. So I'm sorry, like if you want, we can actually talk about it offline. Like I said, you can always book a session with us. And yeah, so let's just get into it. So what is continuous improvement? The first thing is that continuous improvement actually comes in two different flavors. The first one is you hire a task force that is going to be working on the process, a certain area of the process, right? And this is extremely critical, is to define your process to begin with, for which value stream mapping is really effective. And then this task force is going to get in and focus on the specific problem for 3 to 5 days. Unfortunately, sometimes you actually have to stop the production in that area because of the fact that they're working, and also because of the fact that your experts are involved in that and they can't be doing any other work. The other alternative, which is one that we're going to talk about a little bit, and Gianluca will actually not be talking about, I think he's going to focus a little bit more on the task force aspect, is to have a gradual improvement process over time. Now, what that involves is continuous review meetings, which we've talked about in the last masterclass, as well as having a clear message for everybody in the organization so that they understand the mindset of what's going on, so that they understand how to contribute to this process, because your people are probably your most effective tool in this area, where every person that's working on an individual task has very good feedback. And this is also where we need an FMEA involved. So some of the methods that we'll be going over is Kanban, OEE, value stream mapping, FMEA, which is failure mode effect analysis. And there's also two other tools that are extremely effective, which are Gemba walks and PDCA, which is plan, do, check, and act. However, we can't get into those because that is a lot of material to cover, and that will probably be in the next masterclass. As well as based on your questions, I think we're actually going to make a masterclass about an FMEA in general, because there was a lot of, I guess, doubt of how effective an FMEA can be in production. And I firmly believe that it is, I personally have seen a lot of FMEAs in one way or another done in an organization, but they didn't call it an FMEA. So for example, they create a catalog where they have design rules of how to go into production, and that's an FMEA. The only thing is though, is that it's not as rigorously structured as it can be, so we don't quantify the effects of what it does in the production process. So going on to the next thing, what we need to do is, when we think about Kanban, it's a traditional process that has been adopted from automotive. And this is something that lean experts all around the world really like because of the philosophy that your production is pulled by demand. It's never pushed. And what does that mean? What that means is that, like, if you kind of imagine yourself being on top of a part, right? And this part is traveling through production from the raw material all the way to everything that's happening. You're kind of like a camera in POV mode, trying to analyze what's going on, and you don't get moved until the next step of the process actually calls for you. And so you're not being pushed from beginning to end, but you're actually being pushed from end to beginning. And in that fashion, what they do is they create what are called Kanban cards, which request a new product or withdraw a new product because, you know, the last step of your production is shipping. And so the shipping is going to say, hey, we need a part to ship. And then the step before that is going to be like, okay, I'm going to get to it, right? And deliver to you that part. And this goes through the entire production. And of course, what's really necessary in this POV mode is that you have to map the entire process. And that's what we do with value stream mapping. And a really big assumption in Kanban is that the entire production is defect-free. So metal additive is not such a process, right? Metal additive is actually, for the most part, the opposite. And so we don't use the pull demand method. What we do is we actually modify the Kanban. And some of the changes that we make are based on the fact that metal AM is a unique process and that everything is produced at once, right? It's not a serial process like in other things where you qualify every step of the process separately and then you know that everything works. What you're doing is you're changing the microstructure, you're also changing the geometry, and it affects the post-processing steps that are happening downstream. So because of that, because everything is in a serial step, because everything is done at the same time, we have to look at it differently. We have to look at it from a push method. And also, additive systems are the most expensive focus of your production in this context. And so we have to consider that when we try to maximize the OEE, because the system cannot just be waiting for a part, because of course there's going to be delays downstream in terms of delivering that. So it's not an instantaneous on-demand production. And if you do that, however, if you have just a serial production, you're kind of losing the benefits of additive for the most part, right? Because the whole idea is that, you know, this is a more expensive technology, but nonetheless, it actually leads you to having a leaner supply chain. So we have to keep that in mind. So one of the things that we need in Kanban are KPIs. And we've actually defined some of the KPIs that we've used with customers before. So you have the quotation phase where you have order entry, and we can keep track of that in our MES system, or a simple accounting system, just looking at all the orders that have been placed. When it comes to data preparation, we have a production queue, which is something that we've talked about in the last masterclass. The next thing is we have the process where we have the machine overall equipment effectiveness. It's not going to be something that we get into now. We've mentioned in the last class before, as well as parameter wastes. And then we have the product that comes out of the system, and we quantify the number of parts coming out, the part volume, because keep in mind, every batch is different. You can have completely different geometries in one production run. So part volume is maybe a more effective way of quantifying this. We have the number of rejections, which is extremely important. It's the opposite of the output of parts. And then we also have the volume to support ratio in order to appreciate the complexity, and also what part of the process is actually manufacturing output versus the necessary evil support structures. Then we have the process duration, which is something where we actually measure the increments from the nominal to the actual to the real time that it takes to prepare the machine and the data, as well as the total time that it takes to produce the entire part from order entry to delivery. And so when we have these metrics in mind, most of these, like I mentioned here, are you can do in Optimal, or you can actually, to an extent, do it on paper. It is quite difficult, to be honest, because there's a lot of factors that go into every one of these KPIs. But if you keep it simple, I think you can get it done. And as well, like I mentioned, the first step you could use an MES, and I think you guys know some of them. One of the questions I had was, what kinds of systems are there? Well, there's 3Your Mind, there's Link 3D for additive. Now, those software packages are still quite young, but I know that, for example, PreziCast uses SAP, and that's fantastic. SAP has been around for a long time, and it can be integrated with other manufacturers. So that's, I think, a very good alternative. So a very simple example can kind of maybe allude to what we're doing here, right? This is a very, very simplified version of a value stream map. And we have the average times that everything takes for a job, as you can see here, that takes 20 hours in the AM process. And there's a lot of time that you lose in each step because you're waiting for something to happen. Now, one of the things that we mentioned in last class already is that because of the push method, we have what's called the production queue. And so up to that point, what we do is we actually go through step 1, which is customer requirements, the quoting, data preparation, the queue, and then the production process. We mentioned why we need a production queue, but then afterwards, we modify the Kanban style in order to talk about the second thing, which is the pull effect, which is on the other side of the production, which is where we actually focus on the delivery, on the quality control, and all the post-processing steps. The reason why this is so simple is because, of course, every geometry is different. But now notice that the steps actually begin from left to right, and then in the middle, during the AM process, they actually go right to left. And so that part of the production is a pull process. If you can set up your production in this way, you have the best of both worlds. You have the best of additive and you have the best of traditional. And this is our modified Kanban style. So the next thing that we focus on is what if there is a mistake? Because as I mentioned, in a Kanban production, you have to have pull, but you also have to have 0 defects. And so we have to get to that stage as fast as possible or in the most effective way possible. And what we use is an FMEA. Now, FMEA, what it does is it takes some kind of a way that something failed, and it does 3 things in terms of estimating the importance of it. It estimates the severity of the problem, the probability of it occurring, and how easy it is to detect. When we take those 3 numbers, then we multiply them together and we get a risk priority number, and the highest ones are the ones that we address first because, of course, that is the most difficult thing, the most important thing for production. We then go over the improvements and actions, and then we actually check whether that has actually helped, and we keep updating the FMEA database. Now, the improvements actually happen in 3 different ways. We first try to eliminate the failure. The second thing is we try to detect anything that cannot be eliminated, and then we try to minimize the waste if it cannot be eliminated completely. And all of these things are recorded, and after the continuous improvement cycle, we then reassess the SOD and the risk priority number as a result, and then we see if there's anything else that we can do. So this is a living document, and one of the questions that we had is, how do we use this in a metal AM production? Well, the answer is that there's many different kinds of FMEAs, right? And some of those FMEAs are called process FMEA, and some of them are part-specific, or what we call specifically a design FMEA. So when we have these 2 kinds of FMEAs, one of the things that we can focus on is we can basically just say everything into the design FMEA. In other words, the failure of a certain geometry. However, what we recommend is that you actually try to take as many things out of that FMEA and actually put it into the process FMEA. And when we then consider and segment our failures and we label them with machine-specific, material-specific, geometry complexity, volume, build height, build time, then we can actually have a customized FMEA that is accessible for your entire organization from the process side. And we actually take requirements away from the design FMEA and we put them into the process. And what happens then is that as more things are moved into the process, we notice that our design FMEA is actually a lot smaller. It's a lot easier. It's a lot easier to qualify that process that application. And then there's more things in the process, which means that the competence of the organization actually increases. That knowledge is retained. So even if someone leaves, which is, by the way, a question I have for Gianluca, even if someone leaves, you can actually get around to doing to continuing your work very quickly. So what we do in that case is then we segment the issues that we have according to machines, materials, geometry complexity. And one of the challenges that we have in that is how do we quantify geometry complexity? How do we quantify volume, build height, build time? Well, we do have those metrics in Optimal, so that makes it very easy, but that's the thing that you have to consider. And like I said, we're going to get into an FMEA at a completely different time because it's a little bit too much to discuss. But when we do that, when we bring it over to the process FMEA, then we can have a very effective continuous improvement approach where the process that we qualify has that integrated into it, and we don't have to, quote unquote, requalify our process because we have these subsections for every different kind of geometry or material or machine. So yeah, having said all that, I think that's a pretty decent introduction to the whole idea. I wanted to get Gianluca's thoughts on this because of the fact that you know, he has been doing this for a while. The second thing is that they are NADCAP certified, and unlike ISO 9001 or AS 9100, NADCAP is a very serious certification. The reason being primarily because of in 9001 and AS 9100, when you don't have an answer to a technical problem, you basically just say that is not critical to safety or quality, and you will still get the certification. So a lot of manufacturers, even though they have that certification, they have an extreme amount of variability in their production because of the fact that they self-decided not to include these technical challenges, which then leads to problems later on in the future in your production environment. But in NADCAP, that's a lot more difficult to do, and this is why we have Gianluca today. So Gianluca, thank you so much again, and I'll just hand it over to you.
Thanks to you, Matt, for the opportunity. Let me share the presentation. I think that you have to stop your one, Matt.
Done?
Okay. So here we go. First of all, I would like to spend some words concerning my company, so concerning GF and what we are doing in additive manufacturing, just to give a fast introduction and overview of our daily job. So we are working between two different divisions out of three in GF. One is the machining solution. It's a very well-known division that produces mainly known for EDM, wire cut, milling, and turning machine. Let me say, several months ago, we start to work as GF with the 3D system to develop in a partnership our own additive manufacturing machine. So we have the opportunity now to work in an environment that gives us the possibility to print metal part till 5 cube meter. And we start the collaboration with the customer mainly from the design of the component, because one of the most critical things in the expedite of the development phase for sure is to have a component that is printable. So reduce as much as possible for sure the support structure and the technical stuff that make the development phase as short as possible and give us the possibility to move to the qualification phase, reducing the number of iterations. As Matt said at the beginning, we consider the additive manufacturing a full entire process, starting from 3D printing, but including also the post-processing. And in this vision, we include also in our offer the possibility to introduce the milling, the turning, the laser texturing machine, that are an important part to give to the product the final requirement that the customer would like to have. The other division where we are working for is the casting solution. So it's again one of the three divisions of GF, and we combine the know-how that we have since more than 200 years from iron sand casting, aluminum and magnesium high pressure die casting, and precision casting with the acquisition of Precicast, to integrate all the competence concerning the mechanical and metallurgical properties of the material with the post-processing in additive manufacturing. Our main field of application are, as Matt said, aerospace. This is coming from our DNA, because Precicast have for sure focused the greater part of his business in aerospace in the last years, and energy as well, where we divide more or less 50% of the market of the share, so between aerospace and energy. And then we have some application in automotive, mainly at the moment in motorsport and racing. Today I bring one case of a component that has been designed internally to test the initial properties of the machine and what kind of results we can obtain in our process. And I made a comparison between the cost and time for the part itself, so the printing and all the post-processing activities. So as you can see in the left side of the screen, the grade of the costs are related with the printing process itself, because of the amortization of the machines. That for sure is the most expensive part of the process. The cost of the powder, which is the second stuff, and then for sure the space occupation, mainly the main hours, and for the loading and unloading and so on. But almost the 50% of the costs are also related with the post-processing. And even, let me say, in a protected environment, in a qualified environment, you cannot touch your process parameters when we are talking about additive manufacturing. So if we are printing an aerospace component and we reach the qualification of the component, and so the customer approval, we need to freeze the process, we need to freeze the powder, we need to freeze the machine, the equipment used. I cannot duplicate the same part on an identical machine, but I need to requalify the machine itself. But I can work on the post-processing, avoiding the requalification, because requalification means cost, especially in the aerospace field. If you have to requalify an equipment, and so the entire process that produces your round component, you have to demonstrate that the machine is capable to meet the same mechanical properties that the part that the customer would like to have, or metallurgical properties. So you need to repeat, I don't know, the fatigue tests that are extremely expensive, and you need to cover the full entire plate, because in a component like this, as you can see, we covered quite the full entire 500 millimeters of availability that we have on XY direction. So it means that you have to fulfill your plate of specimen, and then you need to test all of this specimen. And as you can imagine, it's something that you need to avoid. So you need to develop a good process, reduce as much as possible the development time, move in the qualification phase, qualify, freeze the process, and then start your production. And the continuous improvement in this case can be applied in the post-production activities much more than in the additive itself. The first thing that you can work on is for sure the process capability. So you need to determine in the pre-serial phase of production, so it's a phase of the production itself, the dispersion of your process in terms of dimensional aspect. And so on the left side you can see a CMM or an Atoscom scanning machine, or in terms of NDT. On the right side there are the X-ray, an X-ray equipment for a round part, and the fluorescent penetrant inspection. So normally you have a customer specification that gives you the limit of the acceptance for the non-destructive test. For example, if you are talking about X-ray or FPI, you will have for different kind of indication a maximum size of defect accepted, while for the dimensional you have a drawing, for sure you have to stay within. So this is normally part of the development. But as said, due to the fact you have to collect the data and analyze the dispersion of your process in a real production phase, this kind of stuff are stressed in the pre-production. And so it could be the case that you have to turn again your process in something that you just have qualified. And here is where we start to talk about really about continuous improvement. The finishing operation for sure are part of the process, because the support removal, especially for the geometries that are not properly designed for additive and where there are some features that cannot be modified because are functional in the part, and maybe it's a translation of a part that has been made always with a traditional production process and need to be switched on additive manufacturing because small series need to be produced. You have just to create the proper support strategy that need to be removed or by manual and so traditional method, or by milling machines, or I put also in EDM work-up machines. So something that we have started now to introduce is the concept of milling directly the part on the start plate to remove as much as possible the support, but also to introduce some reference for the final machining in a phase where you can use the start plate itself as a base plate and so reference for the machining. The precision of the additive manufacturing give you this kind of advantage, especially when you are talking about multiple parts. The last point that I would like to touch is concerning the metallurgical and the mechanical properties, so the metallurgical structure of a component. This is a key topic, because for several kind of alloys, for the most of the alloys, especially if you are focusing again on the aerospace, on the nickel-based alloy, you need to perform a series of heat treatment after the 3D printing. Normally a stress relief to remove the stress from the part and guarantee the separation from the start plate, avoiding the cracks for sure. But then some other kind of treatment like solution or aging to give to the material the properties that the customer wants to have. Second thing for sure is the porosity. So you need to stay within a certain range of porosity in an inspection field that is determined by the customer specification. So if you make a section of one part and you inspect the field in an area of, I don't know, 4 square millimeter, you have to demonstrate that your porosity level is within a certain limit of tolerance. Sometimes it's reached by the process itself, sometimes is obtained by subsequent treatment operation like the orthostatic pressure. What I would like to highlight here is that there are some interesting activities ongoing also from our side to improve the process parameter to give to the material the microstructure that you would like to obtain with the subsequent heat treatment. So you can maybe avoid not the full entire treatment cycle, but some steps to minimize at least the stress, and so to avoid to put in an heat treatment furnace that works under vacuum like the one on the screen, parts that anyway can have some residual of powder that moving inside the diffusion of the furnace can create a lot of critical problems, especially on the technical oil that is used to create the vacuum in this kind of equipment. And so is a very important step forward to obtain something that is, let me say, faster inside your production. So going back to the previous slide and moving on the dimensional aspect, on the capability of the process, on the finishing and on the treatment, you can shrink both the cost and the time, continues to produce a part without the necessity of liquefaction, but demonstrating to the customer that you have a frozen process and that you've improved your post-processing to minimize the impact on the quality of the product and on the time and the cost. I think that's it.
Gianluca, thank you so much. I guess we can open it up to questions, but one of the questions that came up before, you kind of alluded to it, but you know, Georg Fischer is in a very good position because of the fact that you make a lot of machines on your own, right? Mm-hmm. So when you have a problem with the process, you can actually reach out to those people and ask them, you know, what's going on? How could we improve this? Or why is the machine doing this? Well, one of the questions that we had was, how do we actually improve the process when the machine manufacturers are not disclosing information to us, right? So in other words, for the majority of users of this technology, the machine manufacturers are in a very awkward position because they of course have some, you know, developments that they're releasing, and they don't want that to be going out to everywhere because of the fact that this is their IP. However, because of the fact that the part is being, you know, so radically changed in terms of microstructure, we have to understand that, because otherwise, you know, the critical applications, which is a very big niche that aerospace has fulfilled for this technology because it's still very expensive, requires that information. So, you know, right away, the first application space is an industry which demands a lot of quality control and understanding of what's going on. But on the other hand, the suppliers of these components, they don't have the privilege to get this unless they're a lighthouse customer, right? Unless you are a GE or a Pratt & Whitney or a Rolls-Royce, right? They get the privilege of questioning what the machine manufacturers are doing, but nobody else gets that insight. So how do you treat that in your process? I mean, do you just say, we're not going to do that kind of work, or is there some kind of a solution in terms of treating this as a black box?
Is a part of, I mean, each year at the beginning we define a budget for the research and development, because as you correctly said, for sure, once you purchase machine from a different, from a supplier, normally there are package of let's say parameters that you could apply to your component based on the material that you are going to print. But these parameters for sure can be optimized based also on the final properties that you would like to give to your material, no? Because not all of the components, even made with the same base material, need to reach the same level of, I don't know, for example, in terms of tensile properties or creep or fatigue. So we are doing right now an interesting study concerning a new material that, I mean, for sure there are not parameters developed at all in each kind of machine because it's something completely new. And we are trying to test to improve one of the weakest points of the additive manufacturing, that's, for example, the creep, because of the property itself of the process, no? I mean, due to the fact that you are going to create local small welding, you are going to create a microstructure that is made by extremely fine grain. If it would be a casting, we call it chip grain. but is even thinner. And so you increase a lot of the properties. For example, the tensile are absolutely increased, but you have a worsening if you're talking about the grip. And we are doing this kind of tests. So working on the process parameters and making metallurgical analysis, so producing a lot of coupon, making the test, analyzing the structure, and then perform, if needed, treatment to improve the properties of what you would like to do. Then you move in the test phase where you produce a real specimen for the mechanical test. And once you have to do this, you have developed your package of parameters. In some cases, there are some customers that are interested to work with you and so to develop this kind of process parameters for their own materials. So it will become their know-how, and so it will become part of the process itself and of the collaboration that you have with the customer. In another case, it's something that we develop by ourselves to have much more competence to sell on the market. So it's something that we do completely internally, starting from base, maybe even by the producer of the machine, and then we move inside our own field, producing the part as we want.
That's really nice. Now let me throw a curveball on that. Right? Let's say that you have, as you know, sometimes there's like Class A, Class B, Class C components, and your manufacturing and your business model is based on the fact that you are delivering Class A components. Then you realize in the middle of your production or in the middle of your qualification that actually, we can't deliver Class A components because the machine manufacturer has done something in the process that is not that we cannot solve. What do you do then? I mean, this sounds like a very big investment that that goes nowhere at that point.
If we need to develop completely something new, a complete new material, and we have to develop by ourselves, normally it's,
for example, or troubleshoot the process that you have.
Because I mean, normally this is not the case, because as I said before, we work in that kind of field where the OEM are not so much, So if we are talking about something so critical, we need to start to think about the fact that normally we develop the parameters not in 1 or 2 months, but is a job that requires a couple of years, maybe, just to have some concrete result. Because you have to think that the most of the component at the end of the day have to fly, So we have to consider a development period that is completely out of the standard thinking of additive manufacturing, as it's much more closer to the casting, and even worse than the casting, because in the casting there are 2,000 years of experience. The investment casting is one of the oldest production process known. The additive manufacturing is something completely new, so you have to think that the customers stay on the safe side of the river for sure, because, for example, we try to, one of the first projects that they follow was to move one part designed for casting, but at the limit of the castability, and move it to additive manufacturing, And the specification of the component was completely different. The porosity level accepted in the casting was 2%. On the additive was 0.04%. The same component, same function, and not because they have a different behavior, but because we don't know how the material works produced in additive or produced in casting. And to collect this data, this will require here, you can do all the tests that you want, but to have the evidence, to give to the authorities the evidence, you have to perform real engine tests that are extremely expensive. So you need to produce components that then will be tested, and the tests will require months and months. So if you are talking about produce a real component in serial for aerospace, you have to think about that this is not something that will happen in few times. And so, yes, it's something expensive, I agree, but it's not something that you have to own by yourself. Is normally, we have now 2 projects with 2 big OEM in this sense, and our project that we start to follow 2 years ago, and I think that we are just in the early development phase. We just closed the feasibility and we just started the development.
That's awesome. Yeah. Now, tell me this. So moving a little bit broader, right? Let's say that you have the process, you figured out this black box approach regardless. Let's say you have this process set up, and then you have to transfer this process from one machine to another. Now, as GF, you guys are not in the position to be focusing on that, right? But you might have to address that because you need more capacity for a certain application. How do you then ensure the process repeatability, especially when you realize in the middle of it, like, oh my God, we need another machine. And then you start building another machine. And, you know, personally, by the way, I've had this problem a lot of times, right? When we were working on a project, we transferred to another system and then the job crashes and then it crashes and crashes. I mean, do you go into the FMEA? Do you requalify the process? Do you add additional quality control steps? Do you just not build it on another machine? Like, or do you just, you know, throw it out and buy another machine? What do you do?
Once we need to shift from the component from one equipment to the other, even if are identical, we need to consider the equipment as the process. The equipment is the process. So if you need to move to a second equipment, you have to qualify another process. In the aerospace, but also in the IGT field, a new equipment is a new process. It's like moving from casting to additive. It's the same. So you need to restart from the beginning and demonstrate that your equipment is able to produce the same mechanical and metallurgical property that you have on the first one. You don't have, for sure, to start from the beginning, because normally you can copy and paste your parameter. You will have some variation because for sure one machine is not exactly identical to the other. You need to recalibrate. Maybe you need to apply a different scale factor because the scanners can work in a small, tiny different way, but you can anyway highlight some deviation from one to the other. But anyway, you have to consider a completely new requalification. So for our kind of business, because even now in automotive, motorsport, the concept of the qualification are smaller for sure than IGT and for sure than aerospace, but there is the concept of freeze a process, no? And in this sense, even if it's easier, but should happen in a complete short lead time, because the season starts and you have to produce your components. So they provide you the drawing, you provide you 3D model, you have, I don't know, 2 weeks to develop the process, froze everything, and then this will be serial production. And if you have some deviation, you need to correct this deviation in the post-processing. You cannot anymore go back in the additive and modify parameters, even if you know that you can improve something. Because the process is qualified, the parts have run the test in the engine of the car, and they froze everything and say, okay, now you need to work on the post-processing if you would like to improve something, not on the process itself.
Mm-hmm. You know, when you and I talk about the process, I think that for some people there's a different understanding, right? And we have to kind of go back to that step for a second, because when I look at the processes, as you said, the machine is the process, but that's not 100% black and white, right? Mm-hmm. There's this issue where you have certain settings on the machine that just vary over time. So for example, when you have a new scanner put in, you will have different settings for acceleration, deceleration. So that's not a part of the process, right? You have to have it qualified with the end result in consideration. So one thing that I always look at is some people either focus to ignore the fine-tuning jobs, right? Mm-hmm. Which is the dimensional accuracy in the X and Y. And other people say that that is a critical step of the process and we need to have some kind of threshold that we have to meet before we continue in the production. And now I feel like that, what is the guideline from your side? Because you know, I definitely have my own answer, but I think it's very challenging because when you define the scaling, for example, on one application, that's going to be perfect. On another application, it'll be very different. And so you can't define that. You would have to maybe do that in the parts or the design FMEA, right? But again, I know that you're not a fan of FMEAs. So yeah, tell me, how would you approach that? Or what for you is the process that is frozen and qualified, and what for you is, give me a couple examples of what's not, that some people might think is.
Yes, I mean, for the customer, I mean, I didn't work for sure for all the OEM in additive, but considering the customer that I work with, for aerospace, everything inside the machine is qualified once you qualify your job. I mean, okay, for sure not the recorder, but if you, for example, change something, I mean, in the nozzle system for the gas, or if you change something on the sieving, or if you change something on the optical chain, for sure you have to restart the qualification from the beginning, because you are working out of something qualified. For IGT, it's just, let me say, less restrictive. You can modify something on the job, maybe not on the machine itself, but on the job you can you can introduce something new. You can modify a little bit the support structure. And I mean, there is not a general rule, but in my experience, we were able to manage an open discussion with the customer, saying, okay, we would like to make this kind of improvement, we would like to modify this, support this, because we saw that stressing the process, this can cause an higher scrap rate than expected, and this will not oblige us to requalify everything. But again, there is not a general rule, is generally written in the customer specification, and again, is based on the confidence level that the customer have on the process and on the equipment that you are using for this kind of component.
Mm-hmm. So, you know, you actually kind of brought it back to something that I mentioned in the beginning, which is there's different kinds of continuous improvement, right? There's the task force, and then there's the regular improvement as you go over time. So when you mentioned the thing right now that, you know, something is going to have to be modified and you have to get approval from the customer, from my understanding, that's more of the task force approach, correct?
Mm-hmm. Yeah, absolutely. Yes.
So how often does that happen for you?
I mean, not so often, because normally our qualification phase is something that we really go to freeze once we have the evidence that the process is repeatable. No, so if we are talking about again, for the qualification of an aeronautical component, we never did, even if, as said, we are working almost since 2 years in aerospace field with couple of big OEM for 2 interesting projects. We never arrived to the qualification phase, but this is because we are a step-by-step process, because of all the costs and all the steps that you described before. So I moved to IGT to give you an example, because this is much more realistic. For the IGT component, we pass through a development phase where we produce a certain amount of part, limiting as much as possible, but where we have at least the evidence, not about the repeatability, but the goodness of the part obtained. So you don't have any statistical data, but you know that your part is conform to all the specification provided by the customer. Or if not, because it could be also that you will not be able to meet the customer requirement because the equipment or the process itself is not capable to meet the requirement, you open a discussion prior to moving in qualification, asking for a production permit. So a fixed production permit that will give you the possibility to provide the part, even if you have a discrepancy on a certain item. No? This is something that is almost normal, because again, in the investment casting, we have thousands of years of experience, and we know where are the limits of our process. In additive, there is always an open discussion, because the parts arrive from different processes, sometimes from casting, sometimes from machining. So the customer would like to have certain tight tolerance, expecting that your process can reach this, because it's anyways a process made by a machine. But you have to consider the shrink of the material. You have to consider the fact that the laser passes through an optical and so an analogic system because of the scanners. No? And so you can have a variation, and sometimes you cannot simply reach. And again, you can have in the development phase a discussion about the redesign of the part if possible, or sometimes you pass through, the most of the case, we pass through a feasibility, because we would like to demonstrate that we can or we cannot. And so if we cannot, and there are no way to move forward, it's better to say, okay, feasibility, that's it, let's move with another part.
Aha, so I nailed you. I finally got you. So there are applications where you have to say no to the customer.
Absolutely, yes, yes.
Can you give us an example?
I mean, I have a lot of examples because yes, no. I mean, we receive, especially in the early months when we opened the startup. I mean, we would like to understand as well as much as possible the market. No, so we started to prior to the acquisition of GF, we started to produce components for different kind of market segment, no, not just the ones that I said are in our DNA. For sure, the goal was always to arrive to aerospace and IGT, because we use the post-processing of GF Precicast, now GF Precicast at the time Precicast, to complete the component. And so we would like to work in this kind of controlled field. Previously, you talk about the NatCap. NatCap was written since the first day when the company has been open. So it was our goal to reach the NatCap, and we build the system to obtain this. But at the beginning, I mean, we try to produce whatever, and the most of the customers that arrive would like to have a component that was not feasible, or was feasible but was not interesting from the commercial point of view, because is a casting part designed for casting with thicker areas for the flanges that have been designed for the feeding of the part. So maybe was not needed, but was designed because the casting needed to have this to put the gates and to feed the part. And then to redesign completely the part, to release a new drawing, to release new specification was so expensive that the customer said, no, you have to produce the part like this, or it's better that you not produce. So we make the quotation, and then we discovered that the cost of the part was 10 times higher than the actual production cost. And so naturally, we send the offer, and the customer said, no, I'm not interested in this. So
yeah.
At the beginning, this kind of stuff happened a lot. Now, for sure,
a lot of time, yeah.
Yeah, we are in a completely different situation where the customer arrives and most of the time just know what they would like to do. So that doesn't arrive with the part designed for other process and then say, let's do an additive, but arrive with part designed in additive. So with number, with angle not smaller than 40 for maximum 40 degrees C to avoid support structure and stuff like this.
Mm-hmm. Okay, so tell me this: when you're talking about these kinds of projects, right? We had a really cool question, and it's a simple question, but I think the answer is very difficult or very complicated. What continuous improvement tool, in your opinion, that you like the most, or what tool do you guys use the most effectively within PresiCast in order to improve the efficiency and also the quality of the process?
Normally, we monitorize the KPI for sure of the part. So we go to check the quality level of the part. We act especially due to what described till now. So due to the fact that we don't want to touch, especially the process, because avoiding the requalification. We normally work with ATD model, no? So we try to identify, in case of failure, in case of scraps, what are the reasons? So we start to fulfill this form. Normally it's in charge of production. So I start, or with my colleague, we start to fulfill the initial phase, then pass to the quality that validate the content, and then we arrive to the department or to the person that or to part of the equipment that caused the problem. And then we start a discussion to improve, to understand if it was a human mistake or if it was something in the equipment that failed and the reason why it failed, so we can replace the part, we can improve the machine, because we have also this opportunity now. We can also work directly on the machine itself, or is something that I mean is related to the post process. For example, we have a lack of material in some physical lack of material or a deformation, and this is due to a support removal, and why it happened? Because the contact point between the support itself and the part was too stiff. And so what we can do, we can improve, we can modify the post-processing, or is the case to review again the support. So this is really an open discussion, and the tool that we have, I mean, for the continuous improvement, especially if you go back and consider the continuous improvement something when your process is not performance to obtain the part that you want, the tool that we use more is the HD. If you would like, instead of to improve the productivity, so you would like to shrink the time and the cost, and in this case, again, we work with the final requirement of the customer. So the customer would like to have a part like this, go back in the process to see what I can modify, okay, to avoid the requalification, but at the same time maintain the same level of quality. And again, NDT, finishing, heat treatment. I cannot hear you, Matt.
Sorry. Last question. You're a very positive guy, and this is fundamentally a problem for the masterclass. Okay, because we really need the negativity and especially the frustration that everybody feels. And you're the most positive person in the world. So I'm going to ask a very negative question. Okay.
Okay.
are the weaknesses from your perspective of doing FMEA of the process in metal additive? I want negative. Don't put in a positive. I want negative.
I mean, the most negative thing that I can say is that I never use FMEA for the continuous improvement. So I don't.
Why is that?
Yes.
That sounds like a negative. Keep going. Keep going.
No. I mean, I understand. I really realize the potential of the tool, because it's a very good tool, but. I mean, there are so many levels of confidence when we are talking about a new process like additive manufacturing. In effect, is because yes, there are a lot of components that are in severe production, even if since years, no. But this remains a new process. This remains something that we are going to investigate and improve day by day. Is something where there is not a standard. I mean, if you're talking about the machines again, each supplier have his completely own strategy that is different from the other. You cannot find a standard in this method, no? While if you're talking about the casting furnace, is something completely different, because yes, you can have better material, I don't know, better time for the melting, but at the end of the day, the equipment is always the same, no? For additive manufacturing, I found really in the different machine producer. Very interesting and different, completely different idea. It means that is something new. So how can you apply a failure model analysis on something that at the end of the day you don't know so good? So how can you assign a predictivity level? No, I mean, how can you say, yes, the occurrence is 10? You don't know, because you don't know in effect how often this can happen, because even if you have a very deep knowledge of your process, except if you're talking about a machine that is on the market since 15 years, like, I don't know, an Arcam 2X, except of this kind of machine that at the end of the day you know very well, there are too many variants that cannot be taken into account. So I think that in this sense, is not a tool that, in my opinion, and to my daily application, can have a real benefit for the continuous improvement.
Very good. Okay, I really like that challenge, by the way. I'm definitely going to get into that in the masterclass next time. But like I said, if you have an FMEA, the basic principle is that the FMEA is a process FMEA, and that's the constraint. And then within that process, you have these subsections for different machines. And as that experience builds up, that's how you quantify it. And of course, the first time it is a best guess. Mm-hmm. You know, that's why we just have a 1 to 10, and it just seems very arbitrary. But I really like that challenge. You and I will talk about that offline. And Gianluca, thank you so much. I hope that wasn't too hard on you.
Thanks to you.
No, really, thank you for taking the time. And the next masterclass we're going to have is actually finding a profitable niche in metal additive and how we're going to use some performance metrics to analyze that. So, you know, if you're interested, of course, you're more than welcome to join. And yeah, if you guys have any specific questions, please book your session on Calendly, and then we'll get back to you on that, just to give you a hand with whatever you're dwelling on, because like we said in the beginning with the masterclass, the whole idea is to share knowledge and just to give people a hand with what they're doing. So thank you again, Gianluca.
Thanks to you, Matt.
We'll send you a follow-up email about that. Thank you, guys.